This video is about a technique that can tell us whether some series converge or diverge. It's based on the improper integrals that we looked at in the preceding chapter, the chapter on methods of integration. And this is not always applicable, but when it is, it'll give you a yes/no answer as to whether or not a series converges. Suppose you're looking at an infinite series, sum n equal 1 to infinity of an, and you have a variation on a theme of the f of x trick. There's a nice continuous function, f of x, so that if you plug in a positive whole number n, f of n gives you back a of n for n equals 1, 2, 3, and so on. This function f ideally is positive, decreasing, and continuous on the interval from 1 to infinity. If these hypotheses are valid, then you can draw a conclusion. The conclusion is this: the improper integral from 1 to infinity f of x dx, and the infinite series, sum n equal 1 to infinity an, both converge. That could happen. Or the integral and the infinite series both diverge. It's one or the other if the hypotheses of the integral test, as we're going to call it, is true. Now, what this means to me is if all of these hypotheses are true, and I could say, figure out that the infinite series converges, that would automatically tell me the improper integral converges. If the infinite series diverges, the integral diverges, and it works in the other direction as well. If the integral diverges, so does the infinite series. And if the infinite series diverges, so does the integral. Now, I'm going to make the unspoken assumption that the hypotheses that we've talked about are valid, so I don't have to keep saying it over and over again. I want to draw a picture of the graph of this function between x equal 1 and x equal 2. I'm doing 1 to 2, but the same kind of comments would apply to 3 to 4 and 4 to 5 and any positive whole number to the next bigger positive whole number. So to be explicit, I'm just going to draw the pictures for x being between 1 and 2. Function f is decreasing. So as I go to the right, the function values, which are the y coordinates on the graph of y equal f of x, get smaller, yet they're still positive. So I'll indicate that by drawing in these decreasing height graphs here. If I think about the area under the curve that I'm talking about, obviously it's inside this big rectangle, so the area under the curve is no bigger than the area of that larger rectangle. Across the bottom, x goes from 1 to 2, so the horizontal width of this rectangle is always going to be 1 unit, whether I'm going from 1 to 2, or 2 to 3, or 50 to 51, or whichever one of them that I'm looking at. When you're on the graph of a function, the y-coordinate is the function value. So this y-coordinate is f evaluated at 1, but that's supposed to be a1. This is supposed to be f2, but f of 2 is a number 2. So I can express the height of this rectangle in terms of the an's. For this rectangle, the bigger height is a number 1. So the area under the curve, which is no bigger than the area of this big rectangle, area under the curve is no bigger than the height times the width, which is A1. But likewise, if I use the right end, x equal 2, to figure out my height, the area under the curve is bigger than the area of this rectangle because the rectangle is contained within the region between the curve and the x-axis. The area under the curve is at least as big as the width, which is 2 minus 1, times the vertical height, which is a number 2. The area under the curve is at least a number 2. There is nothing particularly special about the interval from 1 to 2 as long as my function is positive, decreasing, and continuous. So if I summarize what we just figured out for the region between x equal 1 and x equal 2, exactly the same kind of reasoning will let you figure out this inequality and that inequality and so on and so forth until the very last integral is the integral that goes from n minus 1 to n. All of these things have to be true, regardless of how big the index n gets. And as a side comment, this integral is the area under the curve from 1 to 2. This integral is the area between 2 and 3. This area is the area between 3 and 4, so on and so forth. This is the area from x equal n minus 1 to x equal n. These regions don't overlap, so that if I add up all of these integrals, I'm just going to get the area starting at x equal 1 and ending at x equal n. That would be the integral from 1 to n of f of x dx. In fact, that's exactly what we're going to do. We're going to add up all of these numbers. That will be less than the sum of all of these numbers, which will be less than the sum of all of these numbers, and we'll begin working towards an infinite series on the one hand and an improper integral on the other hand. So doing what we just said we were going to do, a2 plus a3 all the way out to an is no bigger than the sum of all of those integrals, which is the area from 1 to n, which is the integral from 1 to n of f of x dx, and that can't be any bigger than a1 plus a2 out to a number n minus 1. Two comments here. Comment number 1, this is a partial sum of the infinite series using the a numbers as its basis. This is partial sum number n minus 1 for the sum n equal 1 to infinity an. Secondly, this is almost a partial sum. All you're missing is a1. So think of just putting a1 plus a2 and then the rest of them, and then subtracting the a1 back off to get back what you had. This quantity is not exactly a partial sum for the A series, but it differs from one only by a constant finite amount. So in terms of behavior, it's going to be practically the same thing as a partial sum. Now, we need to know two facts to continue with this. These facts are obvious, but sometimes when you're talking about this sort of thing, it's easy to get lost in things that should be obvious but maybe aren't. So I'm going to explicitly say some facts that we need here. If you're adding up a bunch of positive numbers, which for the moment I'm going to call b sub n, if that series diverges, then there's only one way that it can diverge. It must add up to plus infinity to use horrifically bad numbers. Why is that? Think about the sequence of partial sums for the B series. B1, B1 plus B2, B1 plus B2 plus B3, and so on. Because the B numbers are positive, every time you go to the next partial sum, it is bigger than the previous one because the numbers are all positive that you're adding. That means that the sequence of partial sums for the B series is monotone increasing. For a given sequence, the sequence is either bounded or it isn't. And by the sequence here, I mean the sequence of partial sums for the B series. That sequence is either bounded or unbounded. If it was bounded, the partial sums for the B series would form a monotone increasing bounded sequence of numbers, but bounded and monotone says convergent. And allegedly our B series diverges. So if you're adding up a bunch of positive numbers and the sum diverges on you, the infinite sum, the infinite series diverges. The only way that can happen is if the partial sums tend to plus infinity as the index tends to infinity. As I said, this should be kind of obvious, but if it isn't, we've explicitly said it now. Another fact that's probably obvious, but if it's not, it will be in a second, is this. Suppose you're adding up a bunch of positive numbers, B1, B2, so on and so forth. Suppose the infinite series based on the B numbers converges to some number capital B, an actual real number capital B. Every partial sum for the B series can be no bigger than B. In fact, they have to be less than B. The reason for that's clear though. Suppose that you had a partial sum, B1 out to Bn, and it was actually bigger than capital B. So I've represented it this way on the number line. So this partial sum is a finite distance to the right from B. If you add more little b terms, since they're all positive, you're going to get even further to the right. You're going to get further away from capital B, and there'll be no way for the partial sums to get close to B anymore. So if you're adding up a bunch of positive things, the infinite series converges to some particular number, then all partial sums have to be smaller than the value of the infinite series. That has to be true. Also, the BNs, they could be some simple things, or they could be these integrals that we're looking at. If I'm integrating a positive function, I have to get a positive answer. So when I add up these kind of things, these are like the BNs of the previous page. If the limit of this as n tends to infinity diverges, the only way that can happen is if the integral from 1 to infinity of f of x dx equals plus infinity, which by now you know I'm going to complain about. That means that the limit doesn't exist because the partial sums become unbounded. So returning to what we said, we figured out that partial sum minus a1, partial sum of the A series that is no bigger than the integral from 1 to n of f of x dx, and that can't be any bigger than partial sum number n minus 1 of the A series. So the A series it either converges or it doesn't converge. And I want to look at the consequences of each one of those two things. So thought number one, suppose that the infinite series converges. You take the limit of the partial sums, you get an actual real number, and I'll call the limit S. Because all of our terms are positive, every partial sum for the A series is smaller than S. We just figured that out a minute ago. Now, this says that the integral from 1 to n of f of x dx, which is not any bigger than partial sum number s minus 1, which is not any bigger than s, that tells us that the integral 1 to n f of x dx is bounded above by some constant number s. The sequence of partial integrals, if you want to think of it that way, is bounded. But on the other hand, we just said a minute ago, if you think about increasing the upper limit of integration, these integrals are going to get bigger too, because I'm including more positive integral, more area. So not only is this sequence of integrals bounded, it's increasing too. And here's where we're going to make the first real use of our trick. Bounded plus monotone means convergent. That means if I take the limit as n tends to infinity of the integral from 1 to n of f of x dx, that converges to some actual real number. So we figured something out. Fact number one, if the infinite series converges, then the integral converges. This is a conditional statement. It's one of these if P then Q things. That is logically equivalent to its contrapositive, which is if this is not true, then this is not true. So I get a second fact for free. Not only does if the infinite series converges, then the infinite series converges, guaranteed to be true, but also if the infinite integral, the improper integral, does not converge, if the improper integral diverges, then it's not true that the infinite series converges. If the improper integral diverges, then the infinite series diverges as well. This is all the mileage that I'm going to get out of the statement if the infinite series converges, but there was another possibility. What does it mean if the infinite series diverges? In that case, I'm going to use the left-hand part of our triple inequality that we had, partial sum number n of the A series minus the constant a1 is less than or equal to the integral from 1 to n f of x dx. Because the terms we're adding up are positive, we've seen the only way that the infinite series can diverge is if the individual partial sums tend to infinity as we allow the index to increase. But you see, these integrals are bigger than the corresponding partial sums minus a constant. If the partial sums become indefinitely big, then the integral, being bigger than basically the partial sums, also has to become indefinitely big. So if the sum of the ANs diverges, the limit of the integrals diverges in the same way, and the improper integral diverges to infinity as well. So our results so far, number one came from thinking about monotone and bounded. Number two came from looking at the logical contrapositive of number 1. Number 3 came from the obvious observation that if you've got two sets of numbers, ANs and BNs, you add up some of the ANs and they get big. The BNs are bigger than the ANs, so the sum of the ANs has to get big as well. And the logical contrapositive of statement number 3 is, if this isn't true, then that isn't true. If it's not true that the integral diverges, that is to say, if the integral converges, then it's not true that the infinite series diverges, that is to say, the infinite series converge. If the integrals converge, then the infinite series converges. And this proves what we were saying. Suppose that the infinite series converges, then so does the integral. Suppose the infinite series diverges, so does the integral. Suppose that the integral converges, so does the infinite series. Suppose that the integral diverges, then so does the infinite series. In terms of convergence or divergence, the infinite series and the improper integral act the same. So if I know about one of them, I automatically know about the other one. Also, because of the whole as time goes by thing, it's not really necessary that the hypotheses be true for all indexes n. If an is f of n, and f is continuous, positive, and decreasing for some index bigger than some specific index, capital N, then the infinite series, whose convergence and divergence is not affected by the behavior of a finite number of terms, and the integral starting at where the function starts acting the way you want to infinity, both converge or diverge. If you followed the as time goes by discussion, that should be obvious to you. The easiest example that I can think of is the sum n equal 1 to infinity, 1 over n squared plus 1. The most obvious f function that I can think of is f of x equals 1 over x squared plus 1. It's pretty clear that this function is positive because x squared plus 1 is, and the reciprocal of a positive number is positive. Also, this function is continuous not only for the x's that we're interested in, but for all x's, because it's a rational function and the bottom is never 0 if x is real. The decreasing part may be less obvious, but if you look at the derivative of f, you get the negative of 1 over a positive number times 2x. If x is positive, then this part is positive, and the negative of a positive number is negative. So f prime is always negative when x is positive. So the function is decreasing on the interval that we're interested in. Now, by itself, that doesn't tell me anything yet, except that I can use the integral test. So this infinite series, the one that we're interested in, and this improper integral, those two things either both converge or both diverge. So if I can figure out what happens with the improper integral, I'll know what happens with the infinite series. This is, as always, a limit. Antiderivative for 1 over x squared plus 1 is the arctan function. I'm going to evaluate that at the positive finite number b and the positive finite number 1 and subtract. If you look at the graph of the arctan function, there is no place on that graph where the y coordinate's pi over 2. However, the y-coordinates get as close to pi over 2 as you want, so the limit of this is pi over 2. Arctan of 1 is a constant, it's pi over 4. So do the subtraction, and you find out that the improper integral has value pi over 4. The integral test then says that the infinite series we started with converges. I want to be real clear on something here. The integral test tells me that that series converges, but it doesn't tell me what it converges to. A common mistake is for people to think that whatever the infinite series converges to and whatever the improper integral converges to are the same, but that's not right. The integral worked out to be pi over 4, which to about 6 decimal places is 0.785398. Look at partial sum number 5 for the infinite series. 1 over 1 squared plus 1, 1 over 2 squared plus 1, and so on until you get to 1 over 5 squared plus 1. This works out to be 1/2 plus 1/5 plus 1/10 plus 1 over 17 plus 1 over 26. I put those numbers into my calculator to 5 significant figures. S number 5 is 0.89728. And since I'm adding positive terms, all subsequent partial sums will be even bigger than that. And 0.89728 is not 0.785398. The integral test doesn't tell me what the value of the series converges to, assuming that it does converge. The integral test just gives me a yes or no answer. Does it converge or does it not converge? When we were talking about improper integrals, there was one topic that I skipped over. I decided to save it till now because that section was getting a little long. So here's the premise. I'm going to have p as a positive constant number, doesn't depend on x or anything. And I'd like to think about what happens when I try to calculate the improper integral from 1 to infinity of 1 over x to the p dx. Since x is going to be at least 1, there's no trouble with any discontinuities or anything like that. The function that we're integrating always makes good sense. I want to think about 3 separate cases. Case number 1, positive number p is less than 1. Case number 2, positive number p is bigger than 1. And the only thing that I've omitted is the situation when p is equal to 1, which we'll have to deal with in a different manner than the first two. Firstly, let's suppose I have a positive number, but it's not as big as 1. When I want to calculate this integral, as always, we turn it into a limit of ordinary integrals. 1 over x to the p power is x raised to the negative p power. When you do the antiderivative, you must increase the power by 1. So the new power will be negative p with 1 added to it, which we'll write as 1 minus p in a moment so it doesn't look so strange. You also have to have the reciprocal of the new power, which is where the 1 over negative p plus 1 comes from. We have to look at the limit as b tends to infinity of 1 over 1 minus p times b raised to the 1 minus p power minus, when I evaluate the antiderivative at x equal 1, I just get 1 over 1 minus p. The second part doesn't worry me at all. It doesn't have b in it. So in terms of taking limits as b tends to infinity, this is a constant. It doesn't mean anything to me. This is a constant factor. That doesn't mean anything to me either. It's this quantity that's going to determine whether I get convergence or divergence. Now, for the case that I'm looking at, 0 is less than p is less than 1. Subtract from this, p less than 1, subtract p from both sides. P minus p is less than 1 minus p. 0 is less than 1 minus p, which means 1 minus p is positive, bigger than 0. The reason I want to know that is that's the power that I'm raising the b to. So here, b is going to be some number. You can think of it as being a large number. I raise it to a positive power, so I'm still going to have a large number. As b tends to infinity, b raised to the 1 minus p power tends to infinity. This limit doesn't exist, which is why we write it as plus infinity. Anyway, if 0 is less than p is less than 1, this integral diverges. So this is one established fact that we know now. What I don't yet know is what if p is bigger than 1, and what happens if p is equal to 1. Now, when I look at the next case, the p bigger than 1 case, I'm going to reuse my antiderivative here because I've already figured it out once. There's no need to do it again. So same antiderivative, same quantity, but this time p is bigger than 1. P minus p is less than 1 minus p. 0 is less than 1 minus p. Excuse me, 0 is larger than 1 minus p, that is. It's 1 minus p that's less than 0. So these numbers in the limit that control what's going on are going to be big numbers, big positive numbers that will become as big as you would like to make them. And I'm raising that to a negative power. That would be 1 over b raised to a positive power. As b tends to infinity, b to a positive power also tends to infinity. This limit that I'm interested in is 0. So the integral from 1 to infinity, 1 over x to the p dx, converges if p is bigger than 1. And in truth, I don't really care what it converges to. I just care that it converges to something. The only remaining case to look at is p equals 1. This case can't be used by using the 1 over n plus 1 x to the n plus 1 power because you get division by 0. So we'll just deal with it separately. What if p equals 1? Then we are integrating the integral from 1 to infinity, 1 over x raised to the first power, that is 1 over x, with respect to x. We know an antiderivative for that. That would be natural log of x. I've got to take the limit as b tends to infinity of natural log of x, where I evaluate natural log at 1 and at b and subtract. The natural log of 1, well, firstly, it's a constant, so it doesn't bother me. Secondly, it's 0, so it really doesn't bother me. But as I let b tend to infinity, the natural log of b also tends to infinity. This integral diverges. So the integral from 1 to infinity, 1 over x to the p, where p is a positive constant, converges if p is bigger than 1, and it diverges if p is between 0 and 1, and even if p were equal to 1. That's the last fact that we figured out. What does this have to do with what we've been talking about? If p is positive, f of x is 1 over x to the p. It's not hard to show that this is continuous, positive, and decreasing on the interval from 1 to infinity. So the integral test says the infinite series, the sum n equal 1 to infinity, 1 over n to the p power, converges if p is bigger than 1, and diverges if p is strictly between 0 and 1. And because of case 3, the series actually diverges for p numbers that are bigger than 0 and less than or equal to 1. These kind of series, for obvious reasons, are called p-series. If somebody puts a p-series down in front of you and asks you whether it converges or not, you should feel really happy about that, because if we know this fact, we can just say what the answer is. Previously, we made kind of a complicated argument based on adding up numbers that look like 1 over k plus 1 over k plus 1 plus so on and so forth out to 1 over 2 times k. We figured out from the fact that everything of that type is at least a half that this series diverges, even though the individual terms tend to 0. We can now see this in a much easier way. The sum, n equal 1 to infinity 1 over n, is a p-series. It's the sum, n equal 1 to infinity 1 over n raised to the 1 power. This is a p-series with p equal 1. And because of what we figured out on the previous page, take one look at that and say, that is a divergent p-series. The end. On the other hand, the sum, n equal 1 to infinity 1 over n squared, the things that you're adding up look like 1 over n to the p when p is 2. Because of what we said previously, since 2 is bigger than 1, the series converges. I know that automatically because it's a p-series with p equal 2, which is bigger than 1. Now, don't get confused though. The value of this infinite series and the value of this improper integral are not the same. We've already seen an example of that. The integral test doesn't tell me what this converges to. It just tells me yes or no, does it converge? To finish up today's discussion, I want to look at a slightly more complicated series. I want to look at the sum, n equal 1 to infinity, of the fraction 3n plus 5 upstairs over the product of n plus 1 and n plus 2 downstairs. It's not immediately obvious that I can apply the integral test, but if I can, the most obvious choice for the f of x function would be simply to replace the letter n with x's. Firstly, this function has a couple of bad spots. At x equal -1 and x equal -2, the function becomes undefined. That's no concern of ours because we're only interested in x's that are 1 or bigger. Secondly, the function's obviously positive. If x is at least 1, then 3x plus 5 is certainly positive. So is x plus 1 and x plus 2. What I don't see immediately is whether or not this function f is decreasing on the interval from 1 to infinity, or equally well, if it's decreasing on some interval that starts someplace and goes towards infinity. We need to check that. Increasing and decreasing, as we saw back in Calc 1, can be determined by looking at the derivative. So I'm going to take my rational function and I'm going to calculate the first derivative of it. It's a quotient, so I use the quotient rule, which says the derivative of f is the function on the bottom times the derivative of the function on the top. The derivative of 3x plus 5 is 3, minus the function on top times the derivative of the function on the bottom. The function on the bottom is x squared plus 3x plus 2. The derivative of that's 2x plus 3. And then you have to divide by the square of what used to be on the bottom of the fraction. Divide by x squared plus 3x plus 2 squared. Before I do anything else, I want to make a comment. X is at least 1. X squared plus 3x plus 2 is certainly positive. The square of that's certainly positive. There's no need for me to go into a bunch of multiplying out and simplifying or anything when I'm thinking about that denominator, because I already know it's positive, and really I don't much care about a simple formula for f prime. I just want to see if it's positive or negative. The denominator's positive, leave it alone. On the other hand, the upstairs is not so obvious. I actually do have to multiply out all of this stuff and combine like terms. When I do that, upstairs, every term has a negative coefficient. So I'm going to pull a factor of -1 out front to make things more transparently obvious. We just said that the denominator is certainly positive. If x is at least 1, x squared is at least 1, 10x is at least 10, so the top is at least 1 plus 10 plus 9, which is positive. So regardless of what x is, as long as it's bigger than 1, which are the ones we're interested in, this fraction is a positive number divided by another positive number, which is positive. And then when you take the negative of that, you get a negative number. When x is bigger than or equal to 1, f prime of x is negative, so the function is decreasing, which is what we wanted to see. The integral test can be applied. Now, since I know that it's now legitimate to apply the integral test, I need to calculate the integral from 1 to infinity of f of x. These are limits of ordinary integrals. So I'm going to integrate f of x from 1 to b, and after I've got that finite quantity in my hand, which will depend on b, of course, I'm going to have to take the limit as b tends to infinity. First things first, in order to do these nicer integrals, I need an antiderivative. We've seen this kind of problem before. I'm going to get my antiderivative by using partial fractions. So write down the partial fraction expansion, multiply through by the denominators to get the basic equation. We have two magic x values that we'll put in, x equals -2 and x equals -1. Doing that, we find out that b has to be 1 and a has to be 2. I'm talking my way through that kind of quickly because we've done this before. The thing that I'm integrating could be rewritten as this quantity plus that quantity. So the thing that I'm trying to calculate is this improper integral. Now, you have to be careful about something. Is it legitimate to break this integral up into the sum of these other two improper integrals? The answer is no. That is illegal. It kind of accidentally leads you to the correct conclusion, but the logic is wrong. These improper integrals are limits. This is the limit as the upper limit of integration goes to infinity. This is the limit of something as the upper limit of integration goes to infinity, plus something of that same nature. The only time you can split limit of a sum up into the sum of the limits is when both of them exist. And if you sit down and carry out the calculation, you'll find out that this integral blows up on you, and so does that one. Neither one of these two things exist individually. So it is not okay to split it up into the two limits, although if you mistakenly do so, you accidentally end up with the right answer. So instead, just deal with what you've got. Simple substitutions in the first part, u equal x plus 1, and in the second part, u equal x plus 2, will let you see that an antiderivative for this is this. I have to evaluate this between 1 and b and subtract. So I'm going to have 2 natural log b plus 1 minus 2 natural log of 2, pardon me, 2 plus 1 is 3. Oh, sorry, I wrote the 3 down here, plus natural log of 2b plus 2 minus natural log of 1 plus 2, which is 3. I have to think about what's going on here. This term is a constant. It doesn't have b in it. Neither does that one. Those terms are constants. Their limits exist and are the values of the constants. That doesn't make any difference to me. So I'll write the part that doesn't matter down at this end. Keep in mind, I cannot bust this up into two limits. I just have to deal with what I've got. As b tends to infinity, natural log of b plus 1 becomes arbitrarily large and positive. 2 times that, this first term becomes arbitrarily large and positive. As b gets really big, b plus 3 gets really big. When I add a large positive number to a large positive number, I get a large positive number. So I'm not busting this up into infinity plus infinity. I'm just saying this quantity, as b becomes large minus a constant. This limit, to use horrible language, equals plus infinity. This limit doesn't exist. This limit diverges. The infinite series that we started off with diverges because of the integral test. So what we've learned today, firstly, check the hypothesis. The f of x function has to be positive, continuous, and decreasing. Ideally, you would want that to be true from 1 to infinity, but it's just as good if it's true from some specific number, capital N, to infinity. Calculate the integral from n to infinity, f of x dx. Ideally, but not really necessary, you'd like n to be 1. If that integral is convergent, if this actually gives you a real number for the limit, then the series is convergent as well. If this integral divergent doesn't settle down to a certain particular real number, then the series diverges as well. This is the integral test. In the cases where it applies, it's very convenient, but there are very many series that don't act like this, where sometimes the terms are positive and then negative for a while, and then positive for a while, and so on. You can't use the integral test on a series like that. Also, if the hypothesis of the integral test is true, you are still stuck trying to find an antiderivative, And as we saw in the previous chapter, that can be difficult. So the integral test, when it works, is very valuable, but you can't expect too much out of it. What we're going to want to see in upcoming sections is other ways of telling if a series converges or not. We'll talk about that sort of thing for a while. We'll look at some special series, and then we'll start talking about what we're really interested in, which is putting variables into these infinite series. But for now, I'm going to stop there, and we will discuss things in the next meeting.